Okay, so let's start the stochastic processes. Okay, so first of all we will define the stochastic process. Okay, so as the name suggests, stochastics means a probability. Okay, it means that the outcome of this process is not defined or fixed. It means that in stochastic processes, the process outcome is not predictable. Okay, the outcome of the process is not predictable. It can attain any value. Okay, okay, these stochastic processes actually have a sample space of it. Okay, so let's define the sample space. Okay, we need to understand the stochastic processes, but before we go to the stochastic processes we need to define some basics of it. Okay, so for this we need to understand the sample space. Okay, so what is now the sample space? Okay, the sample space is the actually the set of possible outcomes of a process. For example, the we toss a die. Okay, we toss a die. Now a die has a sample space of 6 events. Okay, it is 1, 2, 3, 4, 5 and 6. So these 6 are the possible outcomes of tossing a die. So when we toss a die, the number that turns out, it can be either 1, 2, 3, 4, 5 or 6. So these are the possible outcomes. Okay, now we cannot define the outcome of it in the real time. We are not sure that the process will give us either 1, 2, 3, 4, 5 or 6 100%. Okay, we are not 100% sure. When we toss a die, there is a probability connected to it. Okay, now these are the total outcomes. Now the total outcomes is equal to 6. Now the probability that we will get 1, probability of 1, it is equal to 1 out of 6. Okay, the probability of getting 2, it is also 1 over 6. Okay, and the sum of these probabilities, it will be equal to 1. Okay, so these are the basics of the stochastic process. I hope you have understood these things. Okay, now we will carry forward the topic and we will go towards the Python process and Python functions. Okay, so let's define the Python distribution. Okay, so the Python distribution actually it models the number of times an event occurs in a fixed interval of time or space. Okay, and we have the assumption that the events occurring are independent of each other. Okay, okay, and are occurring at constant rate. For example, we can define like the number of customers. Okay, this can be done with the example of number of customers entering a mall every hour. Okay, so now the number of customers entering, okay, this is the Poisson distribution. This is defined by the Poisson distribution, and every hour it means that we have a fixed interval of time. Okay, so this hour is the fixed interval of time, and the number of customer occurring is the number of times an event is occurring. The number of customers is the event that we are defining it over here. The function that defines this Poisson distribution is P of x is equal to k. X is the event and k is the number of times that that event is occurring. Okay, and it will be equal to lambda lambda raised to power k e raised to power minus lambda divided by k factorial, while k is equal to 0, 1, 2 up to infinity. This is the number of times that we will define that the event is occurring. Okay, so this is the main function to define the Poisson distribution. Okay, let me write it over here, that what lambda is defining, okay, what is k and what is e. There are three things over here: lambda, k and e. Okay, so this lambda is the average number of, if I define it in the customers, so it is average number of customers occurring at specific time, or average number of occurrences per unit time. Okay, per unit average number of occurrences of any event. Okay, it can be number of customers, it can be number of calls that we are receiving, it can be the number of emergencies that are occurring, it can be the number of earthquakes occurring in Japan every year. Okay, it can be anything, it can be any event. Okay, so lambda is the average number of an event occurring over a certain period of time. Okay, k on other hand is the number of occurrences. Okay, okay, how many time this event is occurring in that time frame. Okay, and e is the Euler's number. Okay, and its value is 2.718 approximate value. Okay, it is constant. Okay, this is variable, and this is constant. Okay, so this is how we define the Poisson distribution. And the real-time example is that the number of calls that a customer support service or customer support center is receiving in an hour or in a day or in 8-hour shift. The time frame or space can be defined as, like, hourly or quarterly, or shift wise, or per day, or you can say per month, any time frame, any space. Okay, so this is the real time example. Okay, so we have defined the probability distribution, its functions, with all its variables and constants, lambda, k, the Euler's number, e, and all. So let's start it with an example. Okay, example for the Poisson distribution. Okay, let me write the formula for it. Okay, probability of x is equal to k, it is equal to e raised to power k, e raised to power minus lambda raised to power k divided by k factorial. This is minus lambda. Okay, or we can just write it as like lambda raised to power k e raised to power minus lambda divided by k factorial. Okay, both are same. So now giving the example, the example says that we are defining the calls to the probability, define the probability that a shopping mall is getting x number of customers per hour. Okay, so in this case we are given that the number of customers, average customers, per hour getting into shopping mall, it is equal to, for example, 50. The shopping mall is receiving 50 number of customers per hour. Now we need to define as what is the probability. Okay, it is equal to lambda. Okay, lambda is this is the rate of customers arriving. Okay, and this rate is defined by lambda. Okay, this 50 is equal to lambda. Now we need to define as the number of customers. Okay, 20 customers. Now we need to define the probability that the 20 number of customers are getting into the mall. So p of x is equal to 20 is to be defined. So we know that p of x is equal to k, it is equal to lambda raised to power k e raised to power minus lambda divided by k factorial. Okay, now k over here it is equal to 20. Okay, so lambda is equal to 50. Okay, the rate of customers, the rate of calls, or the rate of any event, it is equal to lambda in Poisson distribution. Okay, so now putting the values over here, lambda is equal to 50, so 50 raised to the power 20 and e raised to the power minus 50 divided by 20 factorial, it will be equal to that the 20 number of customers are getting into the probability for 20 number of customers getting into the mall. Okay, so if we calculate it, okay, and e is equal to 2.718, this is the Euler's number. Okay, so let's calculate it. Okay, so 550, this 50 raised to power 20, okay, it will give us 9.536 into 10 raised to power 33. Okay, and e raised to power minus 50, it will give us 1.93 into 10 raised to power minus 22. Okay, and 20 factorial, it is going to give us 2.43 into 10 raised to power 18. Okay, so putting all these values over here, we get p of x is equal to 20 is equal to, okay, so 9.536 multiplied by 1.93 into 10 to the power 33 into 10 to the power minus 22. Okay, and divided by 2.43 into 10 to the power 18. Okay, this 10 to the power 18, when it goes in the numerator form, it will give us 10 to the power minus 18. Okay, so 9.536 multiplied by 1.93 divided by 2.43 into 10 raised to the power 33 minus 22 minus 18. Okay, so let's calculate it. Okay, this numerator, this multiplication, it will give us 18.40 divided by 2.43 into 10 to the power 33 minus 22, it will give us 11. Okay, and 11 minus 18 is minus 7. Okay, so this thing 18 divided by 2.43, it will give us 7.57 into 10 to the power minus 7. Okay, so it will give us 0.000000757. Okay, this is the probability of getting 20 customers an hour. Okay, now when we get it into percentage, it will give us 0.005,757% chances that we will get 20 customers in an hour. Okay, the probability is quite low. Okay, so this was a general example. I will give you another example also to understand it. Okay, this is another example 2 for the Poisson distribution. Okay, this tells us that a call center receives 5 calls per hour. Okay, it means that lambda is equal to 5. Okay, we want to know that the number of calls that we receive in an hour, let that suppose be 3. Okay, so the number of 3 calls in an hour, we need to find the probability for this thing. Okay, the probability for receiving 3 calls in an hour. Okay, so it will be equal to the probability of x is equal to 3. It is equal to lambda raised to the power k e raised to the power minus lambda divided by k factorial. K over here is 3. Okay, so lambda is 5. So 5 raised to the power 3 e raised to the power minus 5 divided by 3 factorial. Okay, so 5 cube will give us 125. 5 into 5 into 5. Okay, 125 multiplied by 2.718 raised to the power minus 5 divided by 3 factorial. 3 factorial will give us 3 into 2 into 1. Okay, so let's calculate this thing, 2.718 raised to the power minus 5. Okay, this will give us 0.00674. Okay, divided by 6. 3 factorial will give us 6. Okay, so now multiply this thing and divide it, so we will get the probability that we receive 3 calls an hour. Okay, so this multiplication will give us 0.842. Okay, divided by 6, so it will give us 0.1404. Okay, this is the probability of receiving 3 calls. So when we multiply it by 100, we will get a percentage. Okay, so it will give us 14.04%. There are 14% chances that we get 3 calls an hour. Okay, so this is how the Poisson distribution works. Okay, the Poisson distribution is governed by this equation. Okay, that is the fundamental thing. This equation is governing the Poisson distribution. Thank you. Okay, in this video we will do the theorem 1.1 and theorem 1.2. Okay, so theorem 1.1 actually it states that if or let x and y are random variables having Poisson distributions independently, okay, with parameters mu and v, okay, then the sum of x plus y will be also a Poisson distribution with parameter of mu plus v. Okay, we know in general form, okay, when we talk about the Poisson distribution, we know that p of x is equal to k, it is equal to lambda raised to power k e raised to power minus lambda divided by k factorial. Okay, so in this case lambda is the parameter. Okay, but now we have two random variables, capital X and capital Y. Okay, and both have the independent parameters of mu and v. So p of x is equal to k. Okay, it has the parameter of mu, so lambda will be replaced by mu, so it will be equal to mu raised to power k e raised to power minus mu divided by k factorial. Okay, I will write with parameter mu. Okay, now we have a term called the law of total probability. Okay, now I will explain this in reference to the law of total probability, because we will prove it using the law of total probability. But before that, I want to discuss the random variables actually. What is a random variable? Okay, okay, so first of all let's define the random variables first. Okay, so in theorem we say that x and y are random variables. Okay, so now what is random variable actually? A random variable is a function, okay, or a representation or interpretation of a function. Okay, okay, it is a function actually which associates a real number with each element of sample space. Okay, we have already defined the sample space. Okay, so what does a random variable do? It actually represents or interprets a certain function and gives the function a real value. Okay, associates a real number with each element of the sample space. Now why we say that it associates each element with a sample space? Because a random variable actually, just like a random number, okay, a random numbers, for example between 1 and 9, okay, it can be like for the first instant we can pick 3, 7, 6, 4, 9, these kind of numbers. We can pick it randomly, but it is a random number. It has a distinct value at first glance. But on the contrary, a random variable actually, it does not have a fixed value at the first glance. It picks a certain sample space and then associates a real number to that sample space. Okay, let me give an example. Okay, this is the function. Okay, and this is the first domain. Okay, and then it links to a range of values. Okay, this domain is the sample space. Now, for example, we say that we toss a coin. Okay, for example, I toss a coin, actually tossing a coin. So what can be the possible outcomes? The sample space, the domain can be either head or tail. Okay, the outcome may be like a head or tail. Now what is the probability of getting a head in 2 coins? Okay, or two times flipping the coin and you get the probability for h. Now this thing is random variable. Okay, and this is the function. Okay, it must follow certain function. Okay, the value of this probability we get through a certain function. Okay, and we get a real number for its output. For example, tossing the coin twice. Okay, or tossing 2 coins, for example, 2 coins actually. Okay, so it can have a value of either head head, tail tail, head tail, or tail head. Okay, these are the 4 possible sample space or outcomes. Okay, so now what does the random variable do? The random variable will associate, for example, we defined the number of heads as capital X. Okay, now X is the random variable, and what is it represents? It represents the number of heads in the 2 coins flapping. Okay, now the probability that X is equal to 0, it will give us certain value. Okay, now this thing is the random variable. Okay, it associates the value of a real number. For example, the probability that we get like 0 heads. Okay, 0 heads. Now where is 0 heads? Only this TT. When we have 2 tails, okay, then we get only 0 heads. So the probability that heads is equal to 0 is 1 out of 4. We have 4 possible outcomes. Okay, and we have 1 outcome out of it actually, which gives us a value of heads is equal to 0. So this is the real value. 1 over 4 are 0.25 or 25% chances. There are 25% chances that we get 0 heads. Okay, now the probability of X is equal to 1, that we get at least 1 head. We have head tail and tail head as these two. Also this third one. Okay, but if we are talking about distinctly like X is equal to 1, only 1 head, then we have a probability of 2 by 4 or 50% chances. Okay, now this is the real value given to certain random variable. And what is the random variable? The random variable is the number of heads occurring, capital X. This is the random variable. Okay, I hope you have understand the random variable. Okay, so now carrying on to the theorem 1.1. What does the theorem 1.1 says that? It says that if X and Y are random variables, okay, just like the number of heads over here, okay, but here we have another random variable also, which is capital Y. So if X and Y are random variables having Poisson distribution independently with parameters of mu and v, mu is the parameter of X and v is the parameter of Y, then the sum of X y will also be a Poisson distribution with a parameter of mu plus v. Okay, let me write it also mathematically. Okay, so we will use the law of total probability. Okay, law of total probability is that the total probability is equal to 1. Okay, the total probability is equal to 1. So if the probability that X is equal to 1 is equal to P, okay, then the probability that X is greater than 1 is equal to 1 minus P, because total probability is 1. So all others will give us a value of 1 minus P. If the probability of X is equal to 1 is P, okay, then all others will give us a value of 1 minus P. Okay, it is same like if we have like a coin, okay, and we have two sample space, head or tail. Okay, so when the probability of getting a head, okay, it is equal to 0.5, then probability of getting a tail is 1 minus 0.5, okay, which is also 0.5. This thing is representing this, but in general terms. Okay, in the next clip I will make the proof of this theorem 1.1. okay, thank you. Okay, so continuing through the theorem 1.1 through the law of total probability. Now what we need to find is, we need to find the probability, okay, for X plus Y is equal to n. Okay, earlier what we did was we found the probability of X is equal to k only. Okay, and it was equal to lambda raised to power k e raised to power minus lambda divided by k factorial, okay, which is the Poisson distribution. Okay, now we need to do probability of X plus Y is equal to n. Now we have two variables over here, X and Y, and the total probability is n. So the probability for X is equal to k, okay, then the probability of Y, it will be equal to n minus k, because the total probability is equal to n. Okay, that is the point to be remembered, to be understood. Okay, and this thing, the probability that X plus Y is equal to n, it will be equal to summation of k is equal to 0 up to n. Okay, probability of X is equal to k and Y is equal to n minus k. Okay, so we can separate it, these two, as summation of k is equal to 0 up to n probability of X is equal to k into probability of Y is equal to n minus k. Okay, now remember this thing, probability of x is equal to k, it was equal to using the Poisson distribution, okay, distribution where x is a random variable and its x is a random variable and its parameter is mu, okay, as we defined earlier. We have x and y random variables with the parameter of mu and v, okay. So the first one, x, has a parameter of mu, okay, and it follows a Poisson distribution. So it will be equal to mu raised to power k e raised to power minus mu divided by k factorial, okay. Now the other one, this one, probability of y is equal to n minus k, it will be equal to, now this is random variable y with the what we say, the parameter of, now this is y is a random variable with parameter of v, okay. So it will be equal to, now mu will be replaced by v, okay, k will be replaced by n minus k, okay, n minus k e raised to power minus v divided by n minus k whole factorial, okay. Now putting these twos into this one, what we get is, we get probability of x plus y is equal to n is equal to summation of k is equal to 0 up to n. Now probability of x is equal to k, it is equal to mu raised to power k e raised to power minus mu divided by k factorial multiplied by v raised to power n minus k multiplied by e raised to power minus v divided by n minus k whole factorial, okay. So simplifying this, okay, we need to, what we need to do is we simplify it using the bases of it, okay. If we have mu over here and mu over here, we can add the power, okay. So similarly doing it, what we get is summation of k is equal to 0 up to n, and we have e over here and we have e over here, okay. These two will be multiplied, okay. So taking all of these into the same hood, okay, the denominators will be multiplied and numerators will be multiplied, okay. So mu raised to power k v raised to power n minus k, okay, dot e raised to power minus mu minus v, okay, because base is same, so base will remain constant and these two will be added, okay. So we did the same. Now multiplying and dividing it with n factorial, okay. So what we get is the probability of x plus y is equal to n, it is equal to summation of k is equal to 0 up to n. Now multiplying it with dividing, multiply and divide by n factorial, okay. Let me write it over here, multiply and divide by n factorial, okay. So n factorial into mu raised to power k v raised to power n minus k e raised to power minus mu minus v divided by n factorial into k factorial into n minus k whole factorial, okay. So this n factorial, okay, this will go on this side of the equation, okay, outside of this, summation, it will go there. Okay, so p of x plus y is equal to n is equal to 1 divided by n factorial into n factorial divided by k factorial into n minus k whole factorial. Okay, and it will be equal to okay, and here we have e raised to the power. Okay, this minus will be taken as a sample and it will be equal to minus into minus, minus into plus will become minus, and minus into plus will become minus, so it will get the same value over here, minus v minus mu minus v, but we can write it also as minus into mu plus v. Okay, now we need to do is we also need to transform or transfer this into outside of the summation. Okay, so let's do it. Okay, so probability of x plus y is equal to n, it is equal to 1 over n factorial to e raised to the power minus mu plus v into summation of k is equal to 0 up to n into n factorial divided by k factorial into n minus k whole factorial. Okay, so now this thing, it gives us like n combination of r, ncr, it is equal to n factorial divided by r factorial into n minus r whole factorial. Okay, so we can write it as in this condition. Okay, with the combination of n combination of k, nck. Okay, here we have ncr, this r will be replaced by k because we have k factorial over here. Okay, so it will be equal to nck. Okay, and this will be multiplied by mu raised to power k dot v raised to power n minus k. Okay, okay, now we know that from the binomial expansion that summation of k is equal to 0 up to n factorial divided by k factorial into n minus k whole factorial multiplied by mu raised to power k dot v raised to power n minus k, it is equal to mu plus v raised to power n. Okay, so this thing, this whole term, okay, this term is equal to mu plus v raised to power n from the binomial expansion. Okay, so we will replace it by this thing. Okay, so probability that x plus y is equal to n, it will be equal to mu plus v raised to power n into e raised to power minus mu plus v divided by n factorial. Okay, and what this suggests, if we see it in broader term or when we zoom it out, actually what we get is that it is the same, actually it is the same binomial binomial, I am saying binomial, it is the same Poisson distribution with the parameter mu plus v. Okay, so it is equal to e raised to power minus mu plus v dot mu plus v raised to power n divided by n factorial. Okay, so this is the same, actually it is the same Poisson distribution with the parameter of mu plus v, because p of x is equal to k according to Poisson distribution, it is equal to e raised to the power minus mu, okay, dot mu raised to the power k divided by k factorial. Okay, now here this k is replaced by n. Okay, this k is replaced by n. Okay, and this capital X actually, now we have the what we say that the parameter of this x actually, the parameter is mu plus v. Earlier the parameter was only mu. Okay, this is with parameter of mu, but here if we replace k with n and the parameter with mu plus v, then probability that x plus y is equal to n, it will be equal to e raised to the power minus mu plus v dot mu plus v raised to the power n divided by n factorial. Okay, so this means that if we have two variables, okay, and two random variables, and both of them are having Poisson distribution with parameter mu and v, then their addition actually, okay, will also be a Poisson distribution with the parameter of mu plus v. That is the whole case of theorem 1.1. Okay, I hope you have understood it. I will do another clip for the another theorem, okay, and then will we go to the Poisson processes. Okay, thank you.